EMI-sensitive applications require low-noise switching regulators to ensure precise measurement, reliable communication, and smooth operation. In addition, power supplies must be efficient to extend operating time and reduce heat dissipation. Getting optimum efficiency and low EMI is always a tough challenge and can result in costly project delays, retesting and certifying product to meet stringent CISPR standards. What can be done to reduce high-frequency noise? How can we address EMI problems without any compromise? How can you simplify and accelerate your design process? Introducing Silent Switcher technology by Analog Devices. These regulators bring new levels of performance for synchronous step-down DC to DC converters, offering low EMI and compact designs through high switching frequencies and high efficiency. With support for input voltages as high as 65 volts and load currents up to 30 amps, with high step-down ratios due to low minimum on times, there's a Silent Switcher solution suitable for your application. Silent Switcher 1 technology gets the balance of EMI and high efficiency right. Unique design and packaging techniques achieve low noise, and the two opposing input current loops create opposing magnetic fields, which cancel each other out. Optional spread spectrum frequency modulation also helps to reduce radiated EMI. Silent Switcher 2 adds integrated precision capacitors, hot loops, and ground plane inside a compact LQFN package for even lower EMI. Fewer external components yield a smaller solution size, eliminate PCB layout sensitivity, and accelerate design time. And now, introducing Silent Switcher 3 with ultra-low LF noise, 10 Hz to 100 kHz, and ultra-fast transient response. Silent Switcher 3 enables noise-sensitive applications with increasing current requirements to eliminate the need for an LDO, directly drives sensitive rails with a high-efficiency Silent Switcher 3. Analog Devices Silent Switcher technology simplifies your switch mode power supply designs, allows you to quickly pass noise immunity standards, and improves your entire system performance. Visit analog.com/silent switcher to learn more. Silent Switcher technology. Power you can trust.
A very good afternoon, ladies and gentlemen, and thank you for joining today's webinar by Analog Devices on improving switch mode power supplies using noise-cancelling technology. My name is Ching Hong, your moderator of today. Thank you for spending your precious afternoon all together with us. Now, before we begin, it is my duty to remind all our attendees that you may submit any questions that you might have in the chat box below at any point in time, and that will not disrupt the conversation as well as the flow of the event at all. So feel free to submit your questions at any point in time. Now, questions will be answered towards the end of the webinar presentation. So feel free to raise questions at any point in time, and do remember to stay for the Q&A to have your questions answered as well. Now, in the interest of time, I'm sure we might not be able to answer some of the questions, or you might actually have some more questions after the webinar itself. So feel free to contact us and we can stay connected via the following email, and that is cic.asia@analog.com. That is cic.asia@analog.com. We look forward to having much more productive conversations with you as well. So just to give a little bit of background about ADI, I'm sure many in the industry are no stranger to this global semiconductor leader that bridges the physical and digital worlds to enable breakthroughs at the intelligent edge. ADI continues to combine analog, digital, and software technologies into solutions that help drive advancements in digitized factories, mobility, digital healthcare, combating climate change, and reliably connecting humans and the world. And in today's webinar, we will be taking a technical deep dive, so get ready for that, on improving switch mode power supplies using noise cancelling technology. We will be looking at how to achieve high efficiency while minimizing EMI and solution size, and also how silent switcher regulators can solve specific application challenges, and also how future innovators can stay ahead of the market trends. Now, before we begin the sharing and presentation as well as the Q&A, we'd like to give a big shout out and a big thank you to the following distributors and sponsors in no particular order. Answer Technology, Arrow, Changnam International Limited CNI, Excel Point Systems, Gilanix, Magnica Sci-Tech, as well as WT Microelectronics. Thank you for your generous sponsorship and making this webinar a possibility right here. Now, to usher in today's presentation, first, please allow me to introduce our speaker for today. He is none other than the Senior Manager, Multi-Market Power Business Unit, Analog Devices, and also the co-inventor and design engineer of the innovative silent switcher technology, Daniel Cheng. Daniel currently leads a team that develops high-performance step-down switching regulators and innovative silent switcher technology, of course. He will be providing insight into the performance, the design, as well as the future of this technology, and more importantly, its applicability in markets and applications such as, but not limited to, industrial, instrumentation and measure, communications, automotive, healthcare, energy, and so much more. He will also be discussing how current and future innovations of silent switcher technology help designers achieve their design goals. Without further ado, please allow me to welcome Senior Manager, Multi-Market Power Business Unit, Mr. Daniel Cheng, please.
Today, I'm excited to talk about ADI's latest innovations using what we call silent switcher technology to solve the noise issues in switching regulators and solve your application's challenges. So let's dive right in. So as most of you are familiar, there are two types of power supplies, a linear regulator and a switching regulator. A linear regulator is very simple and yet very inefficient as the voltage drop is across that pass element. A switching regulator instead uses switches and stores energy through a magnetic, like in an inductor, and as a result is much, much more efficient. But inherently, switching regulators produce noise. Today, our examples will focus on monolithic buck or step-down converters though the technology can and is also applied to other switching topologies as well. So what is the problem we're trying to solve? Noise and ringing. Here is a synchronous buck converter. And in a buck, there are two power FETs, M1 and M2. When the top FET is on, the current loop goes through the blue current loop. And when the bottom FET is on, M2, the current goes through this green loop. The node in between the two power FETs is the switch, or what we call the switch node. And that's the node that's rapidly slewing up and down. So as the switches take turns turning on and off and hard switching between each other, the dotted red line represents what we call the hot loop. This is the high DI/dt loop. And when you couple this with all the parasitic RLCs, this results in switch ringing, like the waveform that you see on the right, and EM noise. So where does this high frequency noise come from? Again, you can take a look at this, that switching transitions with parasitic RLs, Ls, and Cs create all these high frequency harmonics. In the time domain, you can see this as switch node ringing. And in the frequency domain, you'll see this as high frequency harmonics. So how do you reduce high frequency switching noise? Well, the traditional way is to slow down the switching edges. You can use just a very slow internal switch driver, or you can add what's known as snubbers externally. This typically is like an RC that you put on that V-switch node to slow down that edge. Naturally and unfortunately, this kind of method drastically reduces the efficiency. You get more switching loss, and especially when you're trying to switch at high switching frequencies, the efficiency really is degraded. So why would you want to run at high switching frequencies? Well, first, this enables the use of much smaller external components, less capacitor, less inductance, and this leads to smaller solution size and less solution cost. And another consideration is in many applications, such as in automotive applications, you want to switch higher than a certain frequency in order to be above, say, the AM radio band. And of course, you can always add filters, and more filters, or you can use mechanical shielding, like putting a big metal box on the whole PCB. But there's obviously downsides to this in component costs and solution size. So the way that we address this challenge is using silent switcher technology. And in summary, silent switcher technology breaks the trade-off between EMI and efficiency by not needing to slow down the switch edges. To illustrate this point, you can see on the right is a plot. It's a bit of a dated plot now, but on the y-axis is efficiency. On the x-axis is switching frequency. And you can see that the ADI switching bucks at the top maintain high efficiency, even at higher switching frequencies, while many competitor parts, while they may look reasonable in efficiency at low switching frequencies, as you increase the switching frequency, the competitor efficiency just plummet. So let's talk about what's behind silent switcher technology. The first three of these are related to package and pinout, and the last one is related to process and circuit design. And so first, we want to reduce the magnitude of the harmonics by limiting parasitics. This is when we made the transition from bond wires to flip chip package technology. Then we reduced the energy in the harmonics by splitting that hot loop into two smaller hot loops. We put them in opposing directions such that the magnetic fields from the two loops actually cancel each other. And this prevents the EMI from radiating and propagating out. And finally, we use an internal powertrain that minimizes the switching loss and produces fast, clean switching edges. Let's step through some of these in more detail. Here is our early old generation synchronous buck converter. As you can see here, there's a single high current hot loop. There's a lot of parasitic inductance from those long bond wires. You can see a SEM photo on the right of an example of a bonded part, and you can see those long, thin bond wires that add a lot of parasitic resistance and inductance to this current hot loop, and that results in a lot of EMI. In our first silent switcher, we removed and replaced bond wires with copper pillar flip chip package technology, which drastically reduces the parasitic inductance. We split the hot loop current into two smaller canceling hot loops, as you can see in the diagram on the left. The green and the blue arrows show the direction of the current loops, and if you recall from physics, the X and the O kind of show the magnetic fields going into the page or out of the page. And so since they are in opposing directions, there is this magnetic cancellation effect. And you put all that together and you get much lower EMI. Here's a cartoon drawing of the magnetic cancellation concept. You can see here the LT8614, which is the buck converter, and the hot loop, the two hot loops on either side to the input, the important input capacitor. And you can see drawn there the magnetic fields directions going in and out. And so if you were to put what we call a sniffer probe or an electric loop above this circuit to a first order, it sees a very minimal or no net magnetic field. And so these magnetic fields are canceling. So our marketing department likes to say, it's almost like enclosing the circuit in a metal box without the metal box. So let's take a look at the results. Here in the time domain, you can see the switch node edge ringing. This is a rising edge, of course, and the 8610 was that first bond wire part that I showed you, and the 8614 is our very first copper flip chip with magnetic cancellation. And you can see that the switch edge is way cleaner, low overshoot, very little ringing. Quick break for vocabulary on EMI. EMI means electromagnetic interference. CISPR is a fancy French phrase for an international committee that takes care of this radio interference. It sets the standards for controlling radiated and conducted EMI. CISPR 32 is the EMI standard for IT and multimedia equipment and replaces the older CISPR 22 standard. Generally, it is less stringent than CISPR 25. CISPR 25 is the EMI standard for automotive market and is an important benchmark for all automotive electronics. You'll see in many of our automotive parts that we always benchmark to CISPR 25 since it is the most stringent EMI standard out there. So moving back to the frequency domain, taking a look at the radiated EMI results, you can see on the left that the 8614 realized a 10 to 20 dB improvement in radiated EMI noise. And on the right side is the most stringent CISPR 25 radiated emission test with the class 5 peak limits in red. And you can see that the LT8614 easily passes this spec. So we were very pleased with these results. It was a significant breakthrough in our switching regulator design. And so we decided to patent this magnetic cancellation concept back in 2014. Unfortunately, over the years, we have seen several copycats. And so I'd like to address that real quick. And what I want to say here is that really not every symmetrical or dual VNIC is a true silent switcher, even if it may look like that. So on the top, we see a very recent part from competitor T, and this is a more latest generation part. They actually have even included bypass capacitors inside the package in order to try to get their EMI better. But what you'll notice in their switching edge is that there's still some kinks and ringing behavior in them. And more importantly, in the frequency domain on the right, the radiated EMI, that this competitor part still is quite marginal or can't quite pass the CISPR 25 spec. So again, not every symmetrical VNIC is a true silent switcher. And that's because in addition to this package and pinout and magnetic cancellation innovation, we've also designed what we call a silent switcher powertrain. And so the next part that we have, the LT8640, took the benefits that we got from the silent switcher package tech and optimized the power stage so that we could also improve the high frequency efficiency while keeping the excellent EMI performance. So on the left, you see a 2 megahertz efficiency plot. The green line is that bond wire part. Again, the orange line is that first silent switcher with flip chip and magnetic cancellation. And the blue line is the next part with the silent switcher powertrain as well. And you can see that we were able to achieve even higher peak efficiency at high switching frequencies. So on the right, you can see the switch node waveform again. Here, if you look at the non-overlap time, you can see that we've reduced it to near zero, and this improves the switching loss pretty significantly. And to dive into that a little bit more, this is what we call zero dead time. Dead time, or the non-overlap time, if you look on the right, is the time when both power FETs are off. In typical in typical switcher design, we turn off the bottom FET, have some delay before we turn on the top FET, and that's to make sure they never cross-conduct or crossbar. Well, with the silent switcher power stage, we've used some circuit innovations in order to reduce that to near zero. And there's some significant benefits by doing that. One, you get less power loss through that body diode conduction. But two, by preventing that body diode from forward conducting, we can minimize the reverse recovery charge, that QRR term. And this obviously results in better efficiency and switching, but it also allows us to optimize the powertrain for controlled and yet fast slew rates of that switch edge. And it, as a result, produces these very fast and yet very clean switch edges. So you can look, here's an example of one of them. You can see that the dead time here is less than 1 nanosecond, but more importantly, that the dead time is low enough such that the body diode never actually forward conducts. The switch node doesn't dip low enough for that to happen. And on the top side, you can see there's very minimal switch ringing, which is an indication of very low EMI. So these switch edges, they look great. We're very proud of them. And so we proudly advertise them in our data sheets. And so you won't see these kind of switch edges probably in our competitor data sheets. So to summarize key takeaways, Silent Switcher 1 allows us to break the trade-off between EMI and efficiency and have both ultra-low EMI emissions and high efficiency at high switching frequency. So moving on to Silent Switcher 2, the next generation. Here we introduce an all-new LQFN package. That's what we call it. And this gave us the ability to integrate the important hot loop and bypass capacitors inside the package. So now all the hot loops, the capacitors, the ground plane are all inside this package, and that leads to even lower EMI. Also, this integration means fewer external components and a smaller solution size to the customer. But all this put together, the key important item here is that it eliminates PCB layout sensitivity. You know, there's many system designers out there that may not be power experts, and oftentimes laying out and designing in switch mode power supplies can be a challenge. Well, with Silent Switcher 2, we've taken that challenge out, and you can feel confident and rest assured that regardless of your PCB layout, that you will be able to achieve excellent EMI performance. So diving into this in some more detail, the LQFN package allows us to also pack in more copper pillars. This means higher efficiency due to lower parasitic resistance and inductance. And we also can achieve better thermals. In the top right, you can see a comparison between a lead frame based flip chip QFN package on the left and the newer LQFN flip chip package on the right. And you can see that this LQFN package allows us to have a more traditional QFN footprint with these large ground exposed pads in the center, which allows PCB designers to pack in a lot of thermal vias and realize great thermal performance. On the bottom right is a cartoon drawing. You can see that we have a straight copper path from the power FET silicon junction directly out of the back panel and onto the PCB board. So kind of putting these concepts all together, here is an experiment we did measuring radiated EMI performance. We removed all the input and EMI filters in order to have more signal. And here are 3 different traces and conditions. The green line, the noisiest line, is where we remove the magnetic cancellation. So essentially we pop off and remove one of the caps on one of the sides. The middle blue trace is a Silent Switcher 1 with just the 2 external input caps. And the red line is representing Silent Switcher 2, which has both internal and external caps. And you can kind of see here more visually the improvement in EMI performance as we step through the generations. One last thing here is about the thermal performance. As I mentioned, the LQFN package enables much better thermal performance. And one of the things I want to bring up is that, not every so-called 10 amp part is truly 10 amps. So here we compare 3 parts. One is the LT8638S from ADI, another is from competitor M, and a third one is competitor T. And while all 3 can provide 10 amps at low switching frequencies, like 400 kilohertz in this instance, if you want to actually switch at 2 megahertz and realize the benefits of higher switching frequencies, while the ADI part can do 10 amps, the part from competitor M can only do 8 amps, and the part from competitor T can actually only do 6 amps. And so this is really a combination of the better thermal performance of the LQFN package, as well as being able to maintain high efficiency even at higher switching frequencies. One other feature that I'll briefly mention here is our Silent Switcher SP line. Here we take that package and we thicken up the die such that we expose the die back to the top. This allows the customer to optionally attach a heatsink mount, or sometimes we see customers want to touch down their metal chassis to the die. And so this will significantly improve thermal performance even more. So to summarize here, Silent Switcher 2 builds upon Silent Switcher 1 by adding integrated capacitors for smaller solution size and even lower EMI. And we eliminate the PCB layout sensitivity. So system designers can have confidence and rest assured that they will be able to achieve excellent EMI performance. So now let's move on to Silent Switcher 3. This is our most recent, latest, and greatest innovation. So you've now heard about Silent Switcher 1 and 2, and we saw how those innovations address the high frequency switching noise and EMI. And Silent Switcher 3 tries to address the low frequency noise now. So this is a bit of a new concept, as traditional or conventional switchers generally don't care about low frequency noise, right? As customers, we think, well, switchers are inherently noisy. So if we have a sensitive application or a sensitive rail, it's going to require an LDO. We're going to have to use LDOs, or we're going to have to at least post-filter the switcher with an LDO. However, here with these silent switchers, we have a fixed frequency peak current mode part with the ability to switch at high switching frequencies. And so we think that we can easily or readily filter that known switching output ripple noise with just a passive post filter and skip the LDO. And one other thing I'll say here is that many and most LDOs do not have great PSRR at high frequencies like the switching frequency anyway. So let's dive into this a little bit more. So why Silent Switcher 3? Well, yes, it's to improve that low frequency noise. And by low frequency noise, I'm referring to what's known as like the 1/F noise, or the broadband thermal or shot noise. So we are trying to improve that part of the noise performance of Silent Switcher. And what we found is in many applications, and this is kind of a market trend, these low noise and sensitive supply rails, they continue to increase in current and power levels. And so LDOs are becoming more and more impractical. And at the same time, system efficiency is also becoming more and more critical as these power levels just continue to increase. So what do I mean by this low frequency noise performance? So to best illustrate this, I've copied in 2 data sheets at the bottom here. You can see on the left, this is the lowest noise LDO on the market. And you can see at the top of the feature list, the critical specs are, that integrated RMS noise from 10 hertz to 100 kilohertz, as well as the spot noise at 10 kilohertz. And so what we've done with SignSwitcher 3 is we've included these kind of metrics onto a switcher, which is a bit unusual, but you'll see that we were able to achieve excellent noise, low frequency noise performance with this new product family. So how did we achieve this SignSwitcher 3? Well, we collaborated with our ultra low noise LDO designers, and we referenced basically their low noise current reference and air amplifier, and we married that with our SignSwitcher powertrain and buck control know-how. And we were able to do this because we have a proprietary internal ADI process technology that has excellent high performance BJTs and really high performance NLDMOS as the power FET. And BJTs are important in this endeavor as they generally have much lower 1/F and broadband noise than their MOS counterparts. Let's take a look at the reference architecture. So on the left is a conventional voltage reference. Here, the buck typically has an internal reference voltage. Here I'm using 0.6 volts as an example. And in order to program the output voltage, the customer simply adds this resistor divider there, RFB1 and RFB2. So for example, if they want a 1.8 volt output, they would use a 3-to-1 divider ratio to regulate the output to 1.8 volts. In contrast, a current reference on the right pins out both inputs of the air amp. And so that reference voltage is actually external. And we provide a very accurate and low noise 100 microamp current source. And the customer programs the output voltage by adding a single RSet resistor. So for example, if you want that 1.8 volts output, you would add an 18K RSet resistor there to program it, to get that programmed Vout. What you'll notice is on that feedback sense line, or the Vout sense line there is no resistor divider. So this is what we refer to as unity gain feedback. So what are the benefits of a current reference architecture? So first of all, you get that unity gain feedback. That means that the reference equals Vout. And so this is important because it means that noise is independent of the output voltage that you're programming. There's no feedback divider factor in there to gain up the reference noise to the output. So using that same voltage reference example again, that internal 0.6 volt noise, 0.6 volt reference, that noise would be gained up 3x if you programmed it to 1.8 volts. However, in a current reference, regardless of Vout, you'll still have the exact same very low noise at the output. The other benefit there is you don't add any resistor noise from the feedback divider itself. So the other thing is by pinning out the reference node, you can put an arbitrarily large C-set capacitor on there to further filter out that low frequency noise. So you can see in the noise spectral density plot at the bottom there, each trace represents an increasing C-set capacitor. And you can see, that the larger the C-set, the lower the noise. A single resistor programs Vout versus 2 resistors in a divider, which can help with tolerance and accuracy. And another unique thing about the current reference is that Vout can be programmed all the way down to 0 volts. So theoretically, you can program your buck converter to regulate a 0 volt output voltage. In a voltage reference, you can only go as low as the internal reference. For example, the 0.6 volts in my earlier example. This current reference architecture is patented by ADI, so you won't see this in any competitor part. So real briefly to look at the feature highlights of the SignSwitcher 3. The first one we've already covered from SignSwitcher 1 and 2. The middle one is that ultra low frequency noise, and you can see the performance, the 1/F noise, and the broadband noise here through the frequency range. And third, on the right, is that Silent Switcher 3 also has very, very fast transient response due to the high gain air amplifier that's BJT based and unity gain feedback. So let's go over these last two features in more detail. So first, the ultra low frequency noise. So here is a table of the integrated noise from 10 Hertz to 100 kilohertz. At the top is the gold standard LDO, the LT3045 at 0.8 microvolts RMS. The first Silent Switcher 3 was called the LT8625S. You can see the comparison between the two in the noise spectral density plot on the right. What you'll notice is that you can get lower noise if you compensate the control loop faster. And the reason for that is a higher bandwidth, a higher compensated bandwidth air amplifier allows it to suppress more of the noise in the control loop. And really, this is also a benefit of switching at higher frequencies because this allows you to comp the bandwidth faster. One of the big takeaways from this slide, though, is that typical LDOs actually have noise in the 20 to 100 microvolts RMS range. And so our Silent Switcher 3 is actually lower noise than most LDOs, and actually lower noise than all LDOs from our competitors as well. The final row in this table is a noise measurement of a Silent Switcher 2 in unity gain feedback. And so you can see that the Silent Switcher 3 has achieved 2 orders of magnitude lower noise than a conventional switcher. And this number, this 123 microvolts RMS number, is in unity gain feedback. So higher output voltages means this just scales up even higher. So here's that plotted visually. This is the noise spectral density plot of a Silent Switcher 3 compared to a conventional switcher through the frequency range. So you can see we're 1 to 2 orders of magnitude better. So let's take an application example. Here we are performing, we're powering one of ADI's really high performance PLLs, synthesizers. And we chose PLLs because the PLLs and clocking chips are one of the applications that are most sensitive to power supply noise. So low phase noise is the critical PLL or clocking spec. And you'll see that a noisy power supply tends to lift up or really worsen that phase noise plot. And so here we've selected a 16 gigahertz PLL frequency synthesizer, and we chose the more sensitive rail, and we are going to do a comparison by powering that with various power supplies. So here's the phase noise plot. This is the kind of the critical metric of a clocking chip, and the blue line is that baseline gold standard LDO, the LT3045. And you can see in red and in black there the Silent Switcher 3 performance at low bandwidth and high bandwidth, and you can see again, you know, if you can comp it faster, you can suppress more noise. So here it's looking pretty good other than around that bandwidth region. So what we do on the right is we add a second stage LC post filter to reduce that noise around the bandwidth. And you can see on the right plot, the red line, which represents the Silent Switcher 3 with a second LC filter, basically achieves nearly the same phase noise performance as the gold standard ultra low noise LDO. So this is pretty incredible. We can do a comparison with other regulators here. On the left, the purple line is a switcher from competitor T. The red line is one of our Silent Switcher 2s in a micromodule. The black line is, you can't really see it since it's covered, but that's our Silent Switcher 3 performance. The green line is the Silent Switcher 3 with the second LC filter. And the blue line in the very back is the baseline LDO performance. And to drive this point home even further, on the right side, you see a phase noise plot of the Science Switcher 3 compared to a more typical or average LDO. And you can see that the Science Switcher 3 is way higher performance. So in summary, Science Switcher 3 can replace LDOs even in the most supply noise sensitive applications, such as PLLs. So looking at this other feature highlight, the ultra-fast transient response, first we look at the RF transceiver power supply requirements. I won't go into this in too much detail. The point here is that there's some stringent requirements in both settling time, transient recovery after load steps, as well as there are circuits that are extremely sensitive to output ripple, noise, and harmonics. This is in the tens of microvolts kind of requirement. And so power supplies that cannot achieve the noise and the timing requirements will absolutely degrade the performance of these LTE and 5G systems. And the other thing to note here is that LDOs are not always that effective at blocking high-frequency spurious content, like all the high-frequency noise, since the PSRR really drops off at high frequencies. So again, powering RF transceivers has a lot of challenges. It requires very fast transient response. It requires extremely low output ripple. And oftentimes the ambient temperatures are quite high, so efficiency is critical. So here we proposed to replace a more traditional buck plus LDO solution with a Silent Switcher 3 solution, which results in much smaller size, lower system costs, better system efficiency, and a huge reduction in ceramic capacitor. So here's a example schematic. And you'll see in the middle, I took a sample where the transceiver has two 1-volt rails, one with dynamic load, meaning there's load steps, and one with a static load, which, a constant load, but requires very, very, very low noise and low ripple, output ripple. So you can see in the dynamic load plot that we're able to achieve this requirement of settling within 0.2% of the final value in less than 5 microseconds. And then on the bottom, the requirement is so low you can't really see anything in the time domain. So we take FFTs of the output, and you can see that it's able to achieve less than the 14 microvolts RMS as well with the second LC filter there. So in sum, you can see that with Science Switcher 3, with the high air amp gain, the unique gain feedback, we're able to achieve really excellent transient response. So changing gears here, here's the ability to multi-phase Science Switcher 3 parts together. Here's a 4-phase Science Switcher 3 application. We put 4 of these parts together, running 1 megahertz each to provide 60 amps at 1 volt out. And you can see the Bodhi plot, we're able to crank up this bandwidth up to over 300 kilohertz with reasonable phase margins still. And as a net result, you can see with even these large load steps and transients, the V out deviation is only 1% and extremely fast. We also see many applications that have very sensitive negative V out rails as well. Often PLLs and ADCs have a negative supply rail that's also very sensitive. And so you can actually use a Science Switcher 3 buck converter in what's known as inverting buck boost or IBB configuration. In the schematic, if you look on the right, you can see that system ground is connected to where V out normally is, and then thus the negative V out rail comes out of where the local ground typically is. And so here's the noise results. In this experiment, we kind of compared it to the latest and greatest Chuk controller converter, since Chuks are known to be low noise, low switching noise for negative outputs. But you can see with Science Switcher 3, we're able to get far lower output noise across the frequency spectrum. And that's the trace in red in that noise spectral density plot on the left. So in summary, key takeaways, Science Switcher 3 builds upon Science Switcher with ultra low frequency noise and ultra-fast transient response. And this new and novel concept is to replace, we want to see if we can replace LDOs or switcher plus LDOs and directly drive with Silent Switcher 3. Since this is our newest portfolio, our first Silent Switcher 3 parts were released a little over a year ago, and we're rapidly expanding this portfolio. The first 3 parts in this table are all pin compatible, and the last 2 parts are pin compatible as well. And so as system designers, you can design your layout or your PCBs, and even if the load requirement from the downstream SOICs may not be known, there's some flexibility here with a bunch of pin compatible parts that you can use. So on wrapping up here is this is an eye chart of all the Silent Switcher step downs we have currently. On the y-axis, you'll see that we have parts ranging from 5 volts to 65 volts, and on the x-axis are the various output current ratings. In blue is Silent Switcher 1, in gray is Silent Switcher 2, in black is Silent Switcher 3. In yellow is this other Silent Switcher family that I didn't have time to discuss today, but it also adds in digital programmability and telemetry via PM bus. So as you can expect, Silent Switcher can apply to many various markets and applications. Industrial and instrumentation has a lot of applications as they very much value high performance, especially at high input voltages. Automotive has had huge growth trends recently with electrification, autonomous driving, and safety, and we see an explosion of automotive electronics, and Silent Switcher is well positioned there due to its low EMI and being able to maintain really good efficiency at high switching frequencies. As you saw with Silent Switcher 3 and the comms communications market, with the intro of 5G and that explosion, we see a lot of opportunities in both wired and wireless applications and comms that can utilize Silent Switcher. And so on and so forth. Many of the similar considerations can be applied to data center, healthcare, aerospace, and defense, etc. So for more information, we encourage you to go to analog.com/SilentSwitcher. And that concludes my presentation. I want to thank you for taking the time to learn about this exciting technology. And I hope for all your upcoming power supply designs that you'll consider ADI's growing line of Silent Switchers. Here at ADI, we are continually innovating to achieve higher and higher performance and solve our customers' greatest power supply challenges.
Thank you, Daniel, for the insightful presentation. I'm sure we learn a lot more and glean a lot more information about the Silent Switcher technology through the presentation as well. Now, I'm sure many of you would have questions pertaining to your own applications in your respective fields as well. And we do have a couple of questions coming in from some of our webinar attendees as well, and we're going to address them. But before that, please allow me to just inform everyone about how this Q&A is going to go. So at any point in time, if you do have questions, which I'm sure you will have, you may type that in the chat box, and we will actually populate the questions and answers over here to be answered. And of course, I will be representing the team to answer your queries as well. Now, in the event, if you do not have enough time to pose a question in the interest of time, we do have an email for you to follow up with more questions later on. And that, of course, comes at the bottom right here. So, of course, feel free to email us with any particular questions or maybe customized applications that you're looking for and any challenges that you are facing. So with that, we're going to kickstart the Q&A session right over here. So we got some questions from the audience as well. So first of all, the SS3 integrates a low noise reference. So how is this normally addressed in a conventional SMPS or even early gen Silent Switcher, for example? Now, so in conventional power design, so a low noise LDO will actually follow the switcher for sensitive rails. So what the Silent Switcher 3 offers is ultra low LF noise as well as ultra fast transient response over the Silent Switcher 2 as well as the Silent Switcher 1. We do hope that clarifies, but of course, if you do need a more in-depth explanation, please feel free once again to email us. Now, we are proceeding on. Let's segue into the second question, shall we? So next up, we have a attendee asking, can you comment on other advantages of higher switching frequencies As a system designer, how should I start thinking about switching frequency when starting a design? Now, first of all, there are several advantages of higher switching frequency. For example, like smaller components and thus smaller solution size. And also the ability to compensate the loop bandwidth faster, resulting in faster transient response, avoiding certain frequency bands. Just think about, for example, the AM radio band in automotive applications, etc. So once again, we do hope that answers your question as well. But for any more specific applications or challenges, do feel free to write into us as well. Now, we're going to go on to the third question over here. And once again, if you do have any questions, please type them in the chat box so we are able to answer them for you specifically. And I'm sure some of the questions that you might have on hand or in your mind will be questions that other attendees are looking forward to hear about as well. Now, next question that we have on hand. Does Silent Switcher 3 integrate the capacitors like Silent Switcher 2? Now, that's a great question. So while the Silent Switcher 3 parts that are released today integrate capacitors like those in Silent Switcher 2, we do plan to release parts that don't integrate capacitors in the future. And that, of course, is in consideration of more cost-sensitive applications. So we do hope that's of help as well. Now, moving on, we have just a couple more questions to go. So next up, what are the additional costs of the various silent switcher technologies? Cost, of course, is one point of concern when it comes to application as well. So speaking about that, so the silent switcher technology does help to reduce the cost of overall CKT. So it offers low noise, high efficiency, high switching frequency, integrated MLCC capacitors, and smaller solution, ultra low LF noise, as well as ultra fast transient response, which we spoke about earlier, which helps to reduce EMI filter design costs. So our all silent switcher parts are all qualified for CISPA 25. So this for CISPA 25 radiated emission test with class 5 peak limit. So these are some of the things that we hope that can help to answer some of your questions as well. Now, I believe we have one more, and this will be our final question for today in the interest of time. But once again, feel free to email us. I will give you the email shortly once more. Now, the final question that we have for today is, do we have a micro module with silent switcher technology? And the answer for that is yes. So for example, LTM8071, LTM8002 are a silent switcher micro module. Now for number of outputs in 1, 2, and 4, it is only available in bulk topology. Now, thank you very, very much for spending time all together with us. Those were some really great questions, very, very insightful, but I'm sure there are more questions pertaining in relevance to your very own application or utility of silent switcher. So for that, once again, we do hope that you can drop us an email, and we can continue to connect at cic.asia@analog.com, and that is cic.asia@analog.com. The next webinar will be coming up very, very soon in July, so do stay tuned and look forward to our announcement and details. We will inform you of the topic and the speaker ahead of time as well. Now, for those of you who might have joined the webinar midway, you might want to catch up on some of the great sharing earlier by Daniel as well. You could essentially go back to the same link on this platform and re-watch the replay of this video. This is all for your convenience as well. So we thank once again the distributors as well as the sponsors who made this possible in no particular order. Answer Technology, Arrow, Changnam International Limited, Excel Point Systems, Gilanix, Magnica Sci-Tech, as well as WT Microelectronics. Thank you once again on behalf of the ADI team. We welcome you to continue to keep in touch with us and look forward to our next webinar. My name is Ting Hong, and signing off over here. Have a great week ahead. See you.